So today we are going to be talking about our first temporary energy storage elements. And so that's going to be inductors. So I'm going to start by boring you guys with a little bit of electromagnetic field theory again. It's not going to be super crucial for you to fully understand where all the math is going. I just want you to have an understanding of what the concepts are. Okay? So for those of you that have taken Physics 202, you may have been introduced, or at least I hope you have been introduced to the fact that if we have a wire that is carrying some current I, we will observe that a magnetic field is going to be generated. So anytime we have charges moving, we are going to generate a magnetic field. And typically speaking, you use what's called the right-hand rule in order to figure out what the direction of your magnetic fields and stuff like that are going to be. So just as a quick explanation, if your thumb is flowing in the direction of current, then your fingers on your right hand are going to wrap around and they're going to show you the direction of the field. So the way that I have things drawn right here, my current I is flowing to the right. So in regions above the wire, I should see that my magnetic field lines effectively come out of the board. So that's what this is. Essentially, we're looking at like the head of an arrow as it's traveling towards us. And then below the wire, we are going to see currents that are flowing into the board. Okay. So magnetic field lines, magnetic monopoles do not exist that we currently know of. So they're always going to form closed loops like this, forming what's called a magnetic dipole, okay? So if we take this a step further, and instead of having just a long straight wire, what if we made a ring of wire and drove some current through that circular loop? So let's choose for our current I to be flowing around this loop in a clockwise direction. So what we would see as we follow our thumb around this path is that outside of the wire, the current would be, or outside of the ring, the current would be pointed out of the page, and inside it was curl down and flow into, so that we'd have something akin to this. And then outside would be our loops like so. Let me move this guy over a smidge. So the reason why I'm bringing these concepts up is because an inductor is nothing more than a coil of wire. So we can treat it as if it is just a stack of those rings up on top of each other, okay? So let me put this in a more illustrative context, okay? So let's say that I have some material. And this is going to be my, what I'm going to call my core material. Typically, this is a ferromagnetic material. Doesn't necessarily have to be ferromagnetic material, but if we want to see a large inductance, it's typically a ferromagnetic material, which has a very, very high, what's called relative permeability. That's a material science thing that we're not going to worry about too much here. It's just going to work to try to enhance the magnetic field of the system, okay? And what we might do to a cylindrical core like this is take a section of wire and wrap it around it a whole bunch of times. Like so. And I'm going to say that there are n number of turns here. And if we connect this coil of wire to some larger circuit and we flow some current, I'm going to call it I of t, going into that top wire, and that same current obviously flows out of this bottom section right here, we are going to cause magnetic field to occur in that stack of coils, right? So that's just a bunch of rings together. If we base everything going on what's happening at the top ring using our right-hand rule, we could see that our current, overall net current, our overall net magnetic field line should be flowing down or something like this, right? So along our central axis, we'll have a straight line, but then as we get away from our central axis, we'll have something like this happening. And we do one on the other side as well, just for the hell of it. Okay. So what this physical configuration does is it tries to essentially compress the magnetic field lines into that region of our core material. So our core has a whole bunch of magnetic field lines flowing through that, and we're going to call that our magnetic flux, where it's typically described by what's called a magnetic flux density. So that's type of field. And it's just the amount of magnetic flux that's flowing around, flowing through any particular surface area. Okay. So this is what's called a solenoidal coil. Okay. I'm going to put here or inductor. And this is one of the most common configurations that we might see. Okay. So anytime we have a current carrying wire, we are going to have some amount of inductance. When we wrap our wire around a form like this to generate a whole bunch of tight coils, we are intentionally introducing a fairly large amount of inductance into our system, and I'll get into the mathematical relationship for inductance here in a moment. One of the principal drawbacks of this particular configuration is that we have what's called flux leakage. So once we hit the ends of that cylindrical piece of core material, our magnetic flux spreads back out and gets lost essentially to the area surrounding the coil. In order to avoid that, there's another type of inductor that you might see very regularly, which is called a toroidal coil. This is going to be a little bit harder for me to draw, but I'll try to do it. It's just because I can't draw concentric circles to save my life. So let's say that we have a donut-like shape like this. If we were to wrap a wire around this donut, we would form another type of inductor. Like I said, this is the toroidal inductor. like so. And if we flow some current I of t down our wire, we are going to wind up having a flux that's just going to circulate around this path. So all of our generated flux is effectively constrained to be inside of this core material in this case, because there are no gaps for it to leak out of. Okay. So this is a toroidal coil inductor. So how many of you all have heard of Faraday's law of electromagnetic induction? Not expecting you to know what it is mathematically or anything like that, but how many of you have ever heard of it? So a couple of people are raising their hands. That's great. So Faraday's law of electromagnetic induction essentially says that an electromotive force, script capital E like this, is going to be equal to, if I'm remembering correctly, negative the derivative of our magnetic flux density with respect to time. So essentially, if I have a magnetic flux that's changing as a function of time, I am going to induce an electromotive force. Electromotive force is just a fancy physics word for voltage, and the physics department would be really pissed off at me saying it that way. But for the intents and purposes of electrical engineers, that's all an EMF is. It's just a voltage. So essentially, if I have a time-varying flux, I should observe a time-varying voltage across the terminals of my inductor. Well, the flux that we are generating is because of our current, right? So we could expand this effectively to say that in terms that we like, our voltage as a function of time, V of t, is going to be equal to L times the derivative of our inductor current with respect to time, where L is our inductance, and it's effectively characterizing how our flux changes as we change the current. Okay. So essentially, what we've got going on here is a form of energy storage. Okay, may not seem obvious yet. It'll seem a lot more obvious, or at least to me, it seems more obvious when we talk about capacitors on Friday. But essentially, because I'm constraining that magnetic field inside that region, I'm storing electromagnetic energy. And then when I allow that to change, I'm either releasing energy out into the system or I'm adding more energy into my storage element, okay? So all an inductor can ever really do is just store energy in the form of the magnetic field lines that are constrained inside of it, okay? So an inductor is going to be our first energy storage element. Yes.
Is there any significance to the pi symbol?
That isn't a 3, that is a B. So that is magnetic flux.
Oh.
So B field is usually what's used to the letter for magnetic flux density field vector, and so phi B is just the magnetic flux itself. So let's look at this guy right here, right? So L is the inductance, and we need to tease out what units this thing is going to have, okay? So on the left-hand side, I have volts. We're just looking at the dimensional analysis here, and we're going to sort things out, right? So on the left-hand side of my equation, I have voltage, which is obviously measured in volts. Then I have my inductance, which I'm trying to figure out what the units need to be. And then I have the derivative of my current with respect to time. So that would be looking like something as amps per second. So what has to go in the middle here is something that's measured in volt seconds per amperes, right? Because if we see this amp cancels this amp and this second cancels this second, then the only thing we're left with on both sides is voltage. So we call this unit of inductance a Henry, where 1 Henry is equal to 1 volt second per ampere, which is the same thing for what it's worth as a Weber per ampere, or an ohm times a second, where the Weber is the unit of magnetic flux. All right. So I want to introduce you guys to the circuit element, not the circuit, the schematic diagram, I guess, representation of an inductor here really quickly. So that's going to be this symbol, okay? Literally just a coil, because all an inductor is, at the end of the day, is just a coil of wire. So we would typically characterize this coil by its inductance value. And then I'm going to define the voltage drop across this inductor as VL, and the current flowing through it is IL. And I've drawn the current flowing into the positive polarity terminal of the voltage so that we know that inductors behave following the passive sign convention, just like everything else that we've dealt with, okay? So this is our symbolic representation of an inductor in a circuit. We've already come up with this relationship from Faraday's law of induction, but I'm going to write it here again. So VL is going to be equal to L di by dt. And this is going to be equation number 1, okay? This guy is really important because it's going to tell us a whole hell of a lot about how an inductor behaves in a variety of systems, okay? So if we have a system where our current flowing through our inductor is constant, what is the voltage drop across our inductor going to be? 0. Why is that? Voltage doesn't go in or out. Voltage is potential difference between 2 points. Try again.
Sorry.
Yeah, so if the current isn't changing, the derivative is equal to 0. Right? That's the point of the derivative. It's measuring the rate of change. So if the current doesn't change, the derivative is 0, and therefore the voltage is 0. So we can expand on this a little bit, okay? So what kind of systems do we know of where the current is a constant? Well, a DC circuit, right? In any DC system, by definition, the currents are going to be constant values. So we can say, just looking at this particular relationship, that in a DC circuit, the voltage drop across an inductor must be 0 volts. So we can take this one step further. What, and I'm using this term loosely, circuit element do we know of that has to have a 0 volt drop across it? A short circuit. So essentially, what we have just figured out is that in a DC circuit, we would just treat inductors like a short circuit or a section of wire. And that should make sense because that's literally all it is. It's just a piece of wire that's curled up into a coil. Okay. Now, let's explore this relationship a little bit further, okay? So let's look at a less boring case where we might have some changing current. So I'm going to draw a couple of graphs here, okay? So let's say, for the ease of math's sake, that I have a 1 Henry inductor. This is the voltage drop across my inductor. This is the current flowing through my inductor. And I'm going to make a plot of the current flowing through my inductor. So this will be IL as a function of time. And then I want us to figure out what the voltage drop across our inductor is going to look like. So this will be VL as a function of time. So let's say that my current starts at 0, and then it gradually increases until it hits some value, stays at that constant value for some interval of time, and then gradually decreases until it stays at 0. Let's throw some numbers at this thing, right? So let's say that this is 5 amps. This point in time is 2 seconds. This point in time is 4 seconds. This point in time is 6 seconds, and so on. So over the interval from 0 seconds to 2 seconds, what should the voltage drop across our inductor be? I'm going to scroll up here so maybe we can have the equation in the same dot. What was that? 5/2, yeah. So there's a rise of 5 amps over a run of 2 seconds. So our slope is 5/2 times our inductance of 1 Henry is going to give us a voltage of 5/2 of a volt, or 2.5 volts. What is our inductor voltage going to be over the interval from 2 seconds to 4 seconds? 0, because our current is constant over that interval. So our voltage is going to abruptly fall down to be 0 volts. And then what is our inductor voltage going to be over the interval from 4 seconds to 6 seconds? Negative 2.5, because our current is decreasing, so our slope is negative, right? And then from 6 seconds and beyond, where our current is a constant 0, our voltage will be a constant 0 as well. Okay. So we've got these set of graphs, okay? So what I want to do is I want to play with our conditions and see if we can suss something out from this, okay? So what if, instead of taking 2 seconds, our current only took 1 second to ramp up from 0 to 5 amps? What would happen to our voltage waveform? So it's going to be squeezed a little bit but it's also going to get taller, right? Because our slope doubled, our voltage will double. So we could keep on playing with this over and over and over again until we got to a situation where we had something like this, where our current instantaneously changed from 0 amps to 5 amps, like so. What would our voltage drop across our inductor be doing at exactly 2 seconds? The rate of change is what? I disagree. What's the rise? 5. What's the run? 0. What's 5 over 0? We're not in a math class. What's 5 over 0? Infinity. Okay. So essentially, if I were able to cause my current to change through my inductor abruptly, what I would see is what are called impulses. Okay. So I would have at t is equal to 2 seconds, a positive impulse where essentially for an infinitesimal amount of time, the voltage drop across my inductor is infinity. And then t is equal to 4 seconds, I would have a negative impulse. Now, is it possible for us to ever achieve, even for a split second, a voltage of infinity? And it's not possible for us to achieve a voltage of negative infinity either, right? So physically, what that would mean is that for that very split second in time, we are transferring an infinite amount of energy to our element, and then we're dissipating that same infinite amount of energy back down. Literally, physically cannot happen. So what this actually tells us is that the current absolutely cannot behave this way in an inductor, or it breaks the laws of physics, okay? So we can say from this little kind of thought experiment, if you will, that the current flowing through an inductor cannot change abruptly, okay? So it needs to take some amount of time for the current to actually change in an inductor. And I'm going to give us kind of a mathematical relationship that's going to help us sort this out, okay? So what I'm going to say is that IL at t minus, so that means as we're approaching just any point in time from the left, must be equal to IL at t plus as we approach that point in time from the right. So from a mathematical perspective, this just means that our inductor current has to be able to be modeled by a continuous mathematical function, right? So no discontinuities or anything like that at any given point in time. Okay. All right, so let's just recap things here really quickly, okay? So we have this first equation. The voltage is equal to L times the derivative of the current with respect to time. From this relationship, we gleaned that in a DC circuit, our inductors are going to behave like short circuits because the derivative of a constant is 0. And in a non-DC circuit, and I'll just leave it there for right now, we know that the current through an inductor cannot change abruptly because that will wind up generating infinite voltages, which obviously cannot happen, okay? So this constraint right here is going to be used by us a whole heck of a lot, especially when we get to the transient analysis stuff that we're going to be talking about at the beginning of next week. This is one of our fundamental rules for how inductors are going to behave in a system where we make perturbations or we try to change things, okay? All right, so before I move on from here, any questions, comments, or concerns? Okay, so the next thing that I want to do is I want to take that first relationship and I'm just going to mathematically rearrange. So essentially, I have an equation that tells me what the voltage is if I know how the current is behaving. So it would be useful to be able to have an equation that tells me what the current is if I know how the voltage is behaving, right? So if I were to mathematically rearrange this equation, I would wind up getting this guy. I'll do it over here. The current flowing through an inductor is going to be equal to 1 over L times the integral from negative infinity to t of, VL t prime dt prime, where those t primes are dummy variables for time. So just because I have the symbol t in my bounds of my integral, I can't also have it be my variable. So that's just a mathematical thing. We did this before when we were looking at the relationship between charge and current. Now, we won't always be able to, or let me put it this way. Integrating from negative infinity isn't always going to be useful or possible, okay? So we might choose to express this integral as 1 over L times the integral from T naught, where T naught is just some point in time where we know what the current flowing through the inductor was, to some later point in time T, a VL of T prime dt prime plus IL at T naught, where this guy right here is what we tend to call the initial condition on our inductor current. So essentially, we can think of an inductor as a circuit element that has some limited amount of memory, because how it's behaving in the present is directly dependent upon what was going on in the past at that time T naught. Okay. So let's look at an example here. Let's work something out, okay? So we can see how this might be used. So let's say that VL of t is mathematically given by the following relationship. 5e to the minus 10t volts. Let's say that L is equal to 3 henries. Let's say that IL at 0 was equal to 1/4 of an amp. And I want to know IL at 3 seconds. So I'm just going to use this equation. I just want to show you effectively how to use it, right? So we would say that IL of 3 seconds is going to be equal to 1 over 3 henries times the integral. So at what point in time is my inductor current a known quantity? 0. So that's going to be my lower limit for my integration. What point in time am I trying to find my inductor current? 3 seconds is going to be the upper limit of my integration. Now I'm just going to substitute in that 5e to the minus 10t volts And I'm going to add to this my initial condition, which is just 0.25 amps. So that addition of the initial condition is happening outside of the integral, okay? So realistically, in this form, we could just throw it into our calculator and call it a day. But sometimes in your homeworks and things like that, we're just going to be trying to find the inductor current as a function of time. So I'm going to walk through this process and all of this kind of stuff, because I will tell you without a doubt, 90% of the issues that you guys are going to face when you're working on these homework problems and stuff like that is going to be issues with units. So I'm going to go through very, very definitively and show you how all the units work out to give us current from this relationship, right? So first thing I'm going to do is I'm going to work on that 3 Henry thing, right? So a Henry, as we discussed earlier, is a volt second per amp. So I'm going to have volt seconds in the denominator and amps in the numerator because I have the inverse of a Henry, right? So this is going to look like 1 amp per 3 volt seconds. Another thing that I'm going to do is I'm just going to pull out that 5 volts, right? So there's a 5 out front and a unit of volts. So I'm going to pull that out of my integration. And I'm left with integrating from 0 seconds to 3 seconds, just e to the negative 10t dt plus 0.25 amps, right? So if we manipulate some things here really quickly, this volt cancels this volt. And so what I have is 5 amps per 3 seconds. And now I have that integral that I have to deal with. So how do I take the integral of e to the negative 10t with respect to time? So my original function, and then I'm going to divide by a factor of negative 10, okay? Okay. So I'm going to have 1 over negative 10. What are the units on that negative 10? I disagree. So the exponential function is going to act on a dimensionless argument, right? But if t is measured in seconds, then that 10 can't be unitless, or the exponential function doesn't work. So if t is in seconds, 10 has to be in per seconds in order for that to cancel out, okay? So this goes back to something that we had talked about way on the second or third day of class. Essentially, anything in an exponential function that's being multiplied by time, assume it has units of per seconds, okay? In your exams and stuff like that, I would just give you a symbol and tell you explicitly alpha, beta, whatever is, 10 per second or something like that. But you're not always going to see that in your homework, so I just wanted to go over it. So anytime we have something multiplied by t in an exponential function, 100% of the time, give it units of per second. So here is a per second. And notice now that this seconds cancels that per second. And so the only surviving unit is amperes, which is exactly what we should expect because we're trying to find current. Now I'm going to have e to the negative 10t evaluated at 3 seconds and 0 seconds, and then I'll do plus 0.25 amps. So let's just play around with this a little bit more. So negative 5 over 30 amps. So the 5 comes from the fact that I already had a 5 in the numerator. The negative 30 is just negative 10 times 3, okay? Then I'll have e to the minus 30. What's e to the 0? 1. Well, that's another thing I see that students make mistakes on very regularly, is just saying e to the 0 is 0. Absolutely not. Brielle, how may I help you? Seconds and per seconds. So seconds and then seconds to the -1 power. Plus 0.25 amps. So distributing this thing through, I'm going to have a DC term of positive 5/30 plus 0.25 minus 5/30. That 5 looks like shit, sorry. Whatever e to the -30 is. And now I'm just going to throw this into my calculator. And I got 0.416 repeating amperes. So on your exams, for what it's worth, the functions that I might give you are always going to be either simple exponential functions or simple sinusoids. So sine, cosine, that's it, right? So as long as you can take the derivative and the integral of an exponential function, a sine function, and a cosine function, you're going to do fine on at least the mathematical part of things. Okay. Does anybody have any more questions about this particular example? Once again, I really just wanted to hammer down what was going on with the units here. Yes. So let me explain this a little bit more formally, right? So I have E to the, let's just call this coefficient for right now, alpha times T, right? Time is measured in seconds. The exponential function can only act on something that is a unitless quantity. So if this T has units of seconds, this coefficient alpha has to have units of 1/seconds or per seconds, right? So in our case, alpha was -10 per second. Will that clarify things, Teresa? Yeah. Seconds over seconds is dimensionless, yeah. Any other questions about this? Okay, so we've got two relationships now. I did not put a 2 here, but that is our second relationship that I expect you guys to have to know. So we've got voltage in terms of current, and now we have current in terms of voltage. So the only other two relationships that we're going to have to deal with is power and energy. Okay. So our power relationship is fairly straightforward. That's just the voltage drop across the inductor multiplied by the current flowing through the inductor. Now I can substitute in what I called equation 1 to replace that voltage and express everything in my power equation in terms of my inductor current. So that would be L times IL times the derivative of IL with respect to time. Okay. So these are our two different representations of how we will calculate power in an inductor. And for what it's worth, I would say 95% of the time, I literally just stick with P is equal to I times V. Brielle, how may I help you? Derivative. Yep. Which is literally what we have up here in equation 1. So the last relationship that I want to talk about is energy. And I didn't bring my notes with me, so I don't know that I'm going to be able to fully derive this. But essentially, the energy stored by an inductor is simply the integral of the power absorbed by an inductor, right? Where this would be goodness, simply the integral of L I di by dt. And we could integrate from negative infinity to some point in time that we're interested in, like so, making these primes if we're paying attention. And essentially, if I were to multiply through by a factor of dt on both sides, I would now have an expression. Let me so that would be the integral from L. I'm probably making a small mistake here, but I'm okay with it because it'll wind up giving us the result we're looking for anyway. I might just upload my actual notes from my office if you care about the derivation. This would be IL at negative infinity, and this will be IL at t. So essentially by multiplying both sides through by dt, my integral on the right-hand side is now I'm integrating with respect to inductor current. And so what that's going to allow me, oh, actually, no. Sorry, this is why it was looking weird. So this is my power. And then these dt's cancel each other out, which lets me switch to that integral. Sorry, that's what I was missing. So essentially, I have the integral of a constant times x dx. So what's the integral of x dx? Yeah, 1/2 x squared. So this is literally just going to come out to 1/2 L IL squared, where we're making an assumption here that the current that was flowing through the inductor at the dawn of time, t is equal to negative infinity, was 0, which I think is a fairly accurate assumption to make. Okay. So this is our relationship for the energy stored by an inductor. So we can determine both power and energy only in terms of current if we were so inclined. Okay. Let me just go through and box all of these important relationships. So these are the 4 equations that govern how inductors behave in a circuit. So just to recap, equation 1 tells us what the voltage is if we know what the current's doing. Equation 2 tells us what the current is if we know what the voltage is doing. Equation 3 is just giving us the power, and equation 4 is just giving us our stored energy. Okay. The only other thing that I want to talk about today, and this will be very brief, is what happens if we have more than one inductor in a circuit. Can we combine them, simplify them, all that kind of good stuff? And the short answer is yes. Okay. So let's say that I had some number of inductors in series. So here's some inductor L1, some inductor L2, all the way out to some inductor L sub n, like so. These are part of some larger circuit. And let's say that there is some time varying voltage drop VT across all of these inductors. And there is some time varying current I of t flowing through all of them. I'm going to express the voltage drop across inductor L1 as V1 of t, the voltage drop across inductor 2 as V2 of t, all the way out to the voltage drop across inductor N as Vn of t, like so. And applying Kirchhoff's voltage law, I could say that V of t is equal to V1 plus V2 plus Vn. So extraordinarily similar to what we saw when we had resistors in series. But now I can express all of these inductor voltages in terms of that current I, but instead of it just being I by itself, like it was with resistors, I have that derivative relationship, right? So this is going to look like L1 times the derivative of I with respect to time plus L2 times the derivative of that same current I with respect to time, because all of these are connected in series, all the way out to Ln times the derivative of I with respect to time. And so I can lump all of those inductor currents, inductors together, L1 plus L2 all the way out to L sub n times the derivative of I with respect to time. And this would be equal to LEQ times di by dt, where our equivalent inductance, LEQ, is simply the sum of L1 plus L2 all the way out to L sub n, or in summation notation, the sum from I is equal to 1 to n of L sub I. Essentially, inductors in series combine like resistors in series. They simply add together. So without doing a whole bunch of calculus, essentially, how do you guys think that inductors in parallel are going to combine? Like resistors in parallel. So we just avoided 4 minutes of math. Great. So an inductor is literally just a coil of wire, right? A resistor is, so it's not necessarily a coil, although sometimes it is, and it's not necessarily a high resistance wire. Sometimes it's carbon films. It's just a high resistance material that we're passing a specific current through here, right? The material is characterized by some resistance, and it's the size of that material inside of that packaging that's actually defining what the resistance is. So sometimes it's a longer strip than others. Sometimes it's thicker, sometimes it's more narrow, just depends on literally what type of resistors. We have like carbon film resistors, metal film resistors, all kinds of different things. So let me just make that last note down here. Inductors in parallel combine like resistors in parallel. All right. So that is enough out of me for today, unless anybody has any questions or anything, in which case I'd be happy to answer them. You guys have an in-class assignment in front of you that is meant to familiarize you with the various relationships and stuff like that that we covered today.